Okay, we're back with part F. So in the last video, we talked through parts D and E, which were very related to one another. I mean, I guess they all are related to one another. It's the same problem, but I know it's a long problem. Okay, so back with the same box, and now we're letting event U. So event U is the event that the second cookie is a butter cookie. Okay, so I want to go into, we're going to find this in many ways. We're going to use the tree diagram, but we're also going to use the formulas, because something that came up when I was talking to one of y'all about this problem was that you technically don't need the tree diagram in order to calculate all of these probabilities, but the tree diagram is very helpful to kind of visualize or check your work, stuff like that, to see different ways to do that. So the probability that the second cookie is a butter cookie. So from the tree diagram, I want to highlight which ones we're looking at. So in this case, we're looking at the probability that we have a chocolate and then a butter, or the probability that we have a butter and then a butter. So if we consider it that way, what we're looking at is we have 21 out of 90 is the probability that we have a chocolate and then a butter, and 42 out of 90 is the probability that we have a butter and then a butter. So let's consider these sample spaces. Again, the only, not sample spaces, events. The only events that fall into U within the sample space would be the events that we have chocolate and then butter, or butter and then butter. Again, this or means we should be adding these. So the probability of U should be 21 over, in fact, sorry, I'll write out what I'm doing. Should be the probability of chocolate butter plus the probability of butter butter. And when we do that, we would get 21 over 90 plus 42 over 90. And that would give us 63 over 90. Okay. So that should be what that probability is. Let's check it in another way. All right. If we write out, like, basically I'm going to break this down into, like, if we were only using formulas. Let's say that I didn't have access to this tree diagram. I didn't want to make it. How would I do this completely by hand without the tree diagram? So I would come back to the fact that this event includes chocolate and butter, or butter and butter. So we've already calculated all these probabilities originally with the tree diagram, but I'm going to break up again if I just didn't have the tree diagram at all, what I would be doing. So this and this, there's like an understood and in between these two. Remember, because we're saying this is like we have a chocolate on the first and a butter on the second. And then that second one is saying that we have a butter on the first and a butter on the second. The or means addition, and means multiplication. So what I'm looking at here is the and this is going to be a very long statement, so I'm going to color code. The probability of U would be the probability that we have chocolate butter, or, which is which is adding, or which is adding, the probability of butter, butter. Okay. But let's break that down even further. So the probability of this one here, remember that's actually the probability that we have chocolate first times the probability that we have butter second, given we ate chocolate already. Then we need to add this, which would be the probability that we have butter on the first times the probability that we have butter on the second, given that we had a butter on the first cookie. Okay, so I'm going to, again, color code. This is this. And as a reminder, we calculated these earlier, but I am doing all of this just to show you how we can do it without a tree diagram. So probability of C times chocolate times the probability of this given, and then we're adding this other thing. So let's go back and get these. The probability that we have a chocolate on this first one given the box we were talking about. So the box, we have 3 chocolate, 7 butter. We're eating a cookie, so without replacement. That first chocolate option, we'd have 3 out of 10 chocolates, or 3 chocolates out of 10 cookies. Then we're multiplying it by the probability that we have a butter cookie. So there are 7 butter cookies there out of 9 remaining. So that's what that is. Then the probability that we have a butter cookie first would be the 7 out of 10, because that's how many butter cookies we have. And we multiply that by the probability that we have a butter on the second, given that we already ate a cookie. So out of the 9 remaining, if we've already eaten a butter cookie, we only have 6 left. So that corresponds to all of those. Let me, I will go up here to keep writing. Okay, so 3 out of 10 times 7 out of 9 would be the 21 out of 90. And we are adding 7 out of 10 times 6 out of 9, which would be 42 out of 90. So we would get 63 out of 90. So either way, again, I know that we were doing essentially the same calculations in both of these methods, but with the second method I was just doing, I technically didn't look at the tree diagram at all. I followed the logic and our formulas for what's going on here. And we got 63 out of 90. So in either of these cases, that's what we're getting. What I want to show now, I meant to make that the same color, but that's okay. Just as a quick extension, what happens if we don't eat the cookie? So all of these have talked about we've eaten the cookie, this is without replacement, etc. So let's make another tree diagram just for that situation to have that discussion. So let's say you randomly select a cookie and don't eat it. And then you randomly select another cookie, let's say after putting the first one back. So I don't know why we would do that. Maybe we picked out a cookie and we didn't like it, so we put it back. So let's just go through this situation. That would change the tree diagram. So the tree diagram before was assuming we ate the first cookie. This one would be we aren't eating the first one. We put it back in the bag. So we'd have chocolate and butter. I'm going to run through this quickly. And I'm not going to color code just for time. We would still have, I'll say, the same sample space with these events, meaning like this one is still chocolate chocolate, this one is still chocolate butter, this one is still butter chocolate, this one is still butter butter. But the difference is the probabilities on this second trial now will be different than they were before because we are replacing it. So if we treat this as with replacement, the first probabilities that we talked about here would still be the same. So getting a chocolate on the first one would still be 3 out of 10. Getting a butter on the first one would still be 7 out of 10. Now what happens though is this chocolate, imagine we pick a chocolate, we put it back in. So this is still the probability that we have a chocolate on the second, given we ate a chocolate on the first. But the difference here is that we replaced it back in the bag. So if I pick out a chocolate, or the box, if I pick out a chocolate from the box and I'm like, man, I didn't want chocolate, I want butter. So then I'll put the chocolate back in. That means the probability is still 3 out of 10 to get a chocolate on the second one, meaning these trials are independent. So here, the probability that we have chocolate is still the probability that we have chocolate on the first times the probability that we have chocolate on the second, given we already picked out a chocolate, but we didn't eat it. So in this case, those probabilities stay the same from trial to trial. In other words, this is equal to that initial probability. We haven't changed anything from trial to trial. So if we do it that way, then we here would get 9 out of 100 for that probability. For the sake of time, I will just run through the rest of these. Butter on the second would be 7 out of 10, meaning there's 7 butters. We hadn't picked one out at all, not that it matters, but there's still 10 cookies left. For this one, there's 3 out of 10. For this one, there's 7 out of 10. So again, that denominator is not changing because we aren't eating the cookie. We just put it back in the box. So then this probability, the probability of chocolate butter, would be 3 out of 10 times 7 out of 10. So 21 out of 100. The probability of butter chocolate would be 7 out of 10 times 3 out of 10. And then this last one, butter, would be 7 out of 10 times 7 out of 10. So 49 out of 100. And again, all those should add up to 1. But that would change our calculation. Like, let's say we went back through and asked all these same questions again, our answers would be different than what we just worked out in all of these videos, because now our answers would be based on the fact that we are not eating the cookie. We are putting it back in the bag after the first one. So I just wanted to talk about the difference between with replacement, without replacement, dependent, independent, and what that would look like for this problem. So that was kind of an extension there. Okay, the very, very last thing I'm going to mention is, like, what if I said, now let's go back to eating the cookie. So assume we eat the cookies. Eating the cookies. What if we ate 3 cookies instead of 2? I'm hungry. I want 3 cookies. What's the probability I got chocolate, chocolate, chocolate? That would be the probability we have chocolate on. I'm going to do it without a formula. Chocolate on the first would be 3 out of 10. Chocolate on the second, if we'd eaten the first one, we'd have 9 cookies left, 2 chocolate remaining. Then I have 8 cookies left because I've eaten these 2. I still want another one. There's only one chocolate cookie left. So then that's how we can calculate the probability of chocolate, 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 or something with 3 trials, for example, without a tree diagram. So you can do it that way. I just wanted to mention that. I won't even calculate what that is. It's math. It's okay. Well, now I feel like I have to. 90 times 8, 6 out of 720. So very low probability that you get chocolate, 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 basically. Okay. That'll be it for these videos. I'm hoping this helps with this, not only the CYU, but with these concepts in general. And yeah, I appreciate you watching. I'll see you later. Thanks.